Okay, let's get started. We have a long list to do today. Generalization, overfitting, are so important for us. Especially when we are working with, robotics and learnings, teachers. Information, this we have a better perception. So what we had last class, we introduced cross entropy. That was one of the amazing loss functions that I'm sure you're going to see later somewhere when it's analyzing actually likelihood. That's bringing impact. We talked about that, how to do multi-class classification. When you have multi-classes, multi-objects, not just two, you can have more than two. We learned that. Softmax was a trick. We're going to have assignments regarding that. See how in practice this works. But today, we're going to talk about generalization. How this model can be generalized. If you learn the robot to move in this room, if you take the robot to another room, it still works. It's called generalization. And anybody else need to sign or mark? Okay. So that's called generalization. And another topic that we're going to cover that is very important is overfitting. Right now that we learn features from data, we need to be very careful. If if the model is too complex, sometimes we can learn some outliers from data as well. We can even learn noise from data because we add noise to data, remember? We just need to learn the pattern, not exact data. That's bringing up overfitting problem that we need to see how we can solve it. One of the ways is regularization. How we can regularize for learning or training to kind of find a balance between complexity and generalization. You need to find that balance. And today we're going to talk about that. It's very important. Something else came up. A couple of the students asked me about validation of that neural network playground. And I'm going to talk a little bit about actually evaluating model, how we can evaluate a model, how we can say this model is good enough. So we can talk about that today. Okay, so let's get us started. First, generalization. We have so many things to say today. I'm going to go a little faster if I can, but you can stop me anytime if you have questions. So generalization means your model not only perform great on training data, but in unseen data, new unseen data. When, as I said, your robot train here in this room with this environment, with these chairs, table, stuff, door, if you take it to the next door, next room, it still works. That means generalization. So it means we need to learn patterns, not all the details of objects. We need to learn patterns instead of, for example, learning from if there is some training data like this, you can learn that as a pattern of circle, or you can learn that even these outliers as a pattern. We want that circle one, that pattern one. Why? Because it's more generalized. If you take that to other room, it still works. However, you need to find a balance. You need to see what is the model for. If your model is so advanced and your environment is so complicated, maybe you want to detect that. Maybe that's the shape of something that you want to model. So that's another story. But generally speaking, we need to make a balance. So generalization means how your model perform good, not just in training data, but on new unseen data. So we need to learn patterns, not exact noise or, outliers. So we need to make training error small, because when you are doing training, you always want to minimize this error, loss function. But also you need to make the testing error small. Testing error means when you test your model in unseen data, the data that's not seen before. The data that you use for training, the model knows everything about that because it's already labeled. But you take this robot to somewhere else, the new data coming, the data that is, they are not labeled anymore. And we need to label them automatically. So that's how a neural network is supposed to work. And that's the trade-off. So in robotic, as I mentioned, the robot trained on leader reading in one room should still correctly detect obstacles in other rooms. But what is overfitting? Overfitting is when the model, instead of learning patterns, learn all the details in training data. Even the noise that you add in purpose is gonna learn that too. If it's too complicated or the features not selected nicely, like this, look at that. This is supposed to be a curve to actually separate these two blue and red dots. But as you can see, the model is so complex and detected all these outliers even with a very complex model. That's not what we want. This is called overfitting. You do over things. Why? Because if you move this model somewhere else, it's not, the noise is not supposed to be like that. It's not gonna detect it. It's not gonna work nice. That's called overfitting. This was for classification. Also for regression is the same too. In regression, you are actually fitting a curve. Like for example, this is a line with some noise, but you're detecting all those outliers as a part of the function approximation. So you found the function that passed from every points of the training data that's not right. So that's called overfitting. So we want to make testing error also low. But as you can see, in overfitting, the testing error is high. So we're going to learn how we can fix that today. The reason of overfitting can be too much parameters and too little data or lack of regularization. We're going to talk about regularization. Regularization is a method to fix that. Regularization means giving penalty to bad features. Giving penalty to the or giving penalty to the weights that are too big. Large weights. We give penalty to those because large weights means too much details. Okay, so let's see what we can do. So this is something that we're going to talk today in robotics. A classifier trained on a specific lighting, for example, or surface texture might fail with changing light. So this is something that we always need to change. The environment situation. Normal things is lighting or texture of the surface that your robot need to act there. We need to test it in different environments to see how it works. Okay. So in this case, for example, the robot learn how to move, for example, in a carpet, for example, when you put that in a tile, probably over there is not going to work properly because it's learn here. So this is called overfitting. So this is happening in real applications. So we need to be careful. Okay, so that was generalization. Something about evaluation we need to talk about. Evaluation means how we check how good is our model. Not just in training data, but in testing data, in the data that is not seen. How we can do that, we need to have some, measuring method. How we measure this, how we evaluate our model. There is some method that we're going to talk today. So normally, when we train data, we learn from training data. But when you want to evaluate, you don't check with training data, you check with the test data. So what is coming to your mind? When you get lots of training data, you need to separate some part for test. Don't touch that part. Don't train the model with that part. That's a separate part of the training data just for test. Still they are labeled. But we use those labeled for testing, for evaluating. We're going to see how we can evaluate that. So we already talked about that. That's a training part. For evaluation, there is two normal, like very general way to do. One is checking accuracy. So we check accuracy, especially for classification problems. We do accuracy with fraction of correct prediction. We can't, for example, if the robot can detect between 100 objects, for example, the robot detecting like 80% of those objects detected correctly. So accuracy is 80%. There is for regression, when you are measuring the value of something, not type of things, you can use mean square error all the time. That's normal. You can use mean square error to see how, if the mean square error is close to 0, so it means good. There is another metrics that you can use, that is R squared. R is coming from correlation. So you want to see how correlated is that. We're going to talk about that. So these are metrics that we can use for evaluation. So evaluation is important. They're just famous metrics. We have lots of other metrics that you can use those. So if I tell you in one of projects, evaluate your result, you need to go in this if they work. If not, you can find another metrics. But they are mostly works for classification, accuracy checking, for regression. Mean square error is a very normal way to check how good is your model. So what is accuracy? Accuracy is number of correct predictions over the total a number of samples. As I said, for example, between 10 targets, your model can detect 8 of them. So it's 80% accurate. So that's simple. That's for actually classification. For regression, we always can use mean square error. Mean square error is, we just need to, if you remember what was the formula for mean square error, mean square error was the average of the square of your prediction from the true data. For example, y hat I, a square. However, this difference, actually this is slow. This is norm 2, and from I to 1 to n, if you have n, for all training data, for testing data. This is for testing data. We are in testing data anymore this time, okay? So we are, for all testing data, we check what is the true value, because we know true value, because they are still labeled. We know what is the true value and what is the or prediction. We make actually least square, the mean square, sorry, we find the mean square, and we average that, and that is the good metric to see how close is your prediction with the true data. If it's close to the 0, that's a good. If it's not, that's not good. There is another metrics that you can use, and that's called actually R square. That's more advanced, and that's actually checking variation, checking determination or uncertainty. Checking answer is coming from correlation. What is correlation? Correlation showing two samples how related to each other. We want to check this one. The formula for correlation, the formula for correlation is this. Correlation is, it's actually in probability if you had that course, but if you not, you take that course, please. There is a very important course, probability and stochastic processes. If you get a chance, take that. So normally correlation is covariance between y and y hat over actually just variance of y hat. Variance showing how one variable varying for itself, but covariance talking about two variables, how these two variables regarding each other changing together. So this is the formula that we need to use For covariance part, we can use exactly mean square error. For variance, we just can use find the mean. And so I'm not going to go deep on that, but you're going to use that for your project. And in your project, probably you're going to see that more. Okay, I'm not going to go more deep on that. It's not very... there's lots of details. Okay, so, but yes, we said we need to find the best place to choose how complex we are and how general we are. How we can choose that? With hypothesis class. If you remember, we talked about, I'm going to bring this one. We talked about this set. We said all predictors on the world. For example, imagine it's this set, this pink one. I don't know if it's pink. Yes, pink. And this pink is all predictors on the world. And for our case, based off the features that we choose, we have this F, this capital F, that is based off our features. We call that hypothesis class. Remember? We call that hypothesis class of our predictors. So for all the predictors, we choose the predictors regarding our features. Based off our features, we select that. And based off that features, we use, for example, one method like gradient descent to find this prediction, F hat. Okay? So, but in this case, we have two different errors. One error is coming, this F hat, it might not be exact, the best F in this hypothesis class. Because, for example, our method that we use for optimization not correct. So anyway, we have some prediction error or estimation error. Estimation error is the error between your prediction and the best prediction in your hypothesis class. So we call that estimation error. Estimation means prediction. Prediction error. So error between our model and the best model in hypothesis class. What is hypothesis class? Hypothesis class is a class regarding your features. You choose these features, you have this hypothesis class. Okay, so that's one error. You have another error. There is somewhere in reality exists an optimal predictor. This optimal predictor is the best predictor ever. It's out of our hypothesis class. So we have another error between actually your prediction and that prediction. That's called approximation error. So these two errors together actually making like all errors that you have. And if you eliminate, so this approximation error coming from error that you had from actually I think I wrote here. So this is approximation error. Approximation error is the error between the best predictor in your hypothesis class to that optimal predictor. So I want to check if I wrote here correct. So this error is, oh, okay. So this error is this, I think. And this error is this. Yes, yes. If you consider that error of G, and this error of F star, the approximator error is this one. Anyway, it's not very important. So the important part is these two errors are actually errors that coming from the hypothesis class size. And hypothesis class size coming from the number of features. When your number of features increase, when the system becomes complex, this purple set becomes bigger and bigger. So when this becomes bigger, the approximation error gets smaller, but estimation error gets bigger. That's why we have a trade-off between these two. And this trade-off, we need to see how we can find it. So we have two errors, approximation error and estimation. When we increase the hypothesis class size with adding more features and more complexity to the system, approximation error decreased, but estimation error increased. So the trade-off is to find a balance, a good place to actually choose what is the size of the features should be. The size of the feature is important. Okay, so because size of the feature specify this estimation error. Okay, so how we can control this hypothesis class size? There is so many ways. One of the ways to actually adjust capacity of the model. Adjust capacity of the model means, for example, you see how detail I need, how much detail I need. Am I detecting just the objects, or I'm detecting shape of the objects, for example? That's two different questions. You know, if you are detecting shape of the object, you should have more complex model than just object. And another method so we can recognize that and design or model based on. Another thing is regularization that we're going to talk today is amazing method. A regularization means giving weight. Regularization means giving penalty to big weights. We give more penalty to bigger weights. Bigger weights means the weights that makes the system complex. And that's regularization. We're going to see that, how we can do that. And feature selection, we can choose feature selection instead of using very simple features. We add a little complex, not complex features, like more meaningful features. Because the features that are related to each other, we can remove them. You know what I'm saying? Some features are related together. We don't need to have them all and make the size of the features big and size of the hypothesis class big and make the error bigger, like estimation error bigger. How we can do that is possible. If you are just using, for example, X and, for example, just complete measurements, maybe you get some principal information from those measurements. Principal components are the features that are not correlated. At least take the things that are not correlated, not depend each other. That's called feature selection or feature extraction. We can talk about that as well. Let's first go for dimensionality. So dimensionality means when you have too much features. If you have too much features, your dimension is a lot. So feature selection is important in this case. And dimensionality is in this picture, as you can see. Instead of, if it depends the model. If your model doesn't need, for example, all of those details, and you just want to check or find the patterns of those data, doesn't need to have very high dimension features. And that also brings higher dimension for weights. So instead of having, for example, 3D dimension, you can make it two-dimension. So that's dimensionality. Dimensionality is important. But you need to find that trade-off. That's important. You need to find that trade-off. Maybe your model need to be 3D or 3-dimension. Maybe it's based off the model, based off the project. And fewer feature, less variance, and more stable. So it's normal and force model to capture essential structure rather than the noise. So if the dimensionality lower, so you can learn more structure of data instead of just the details. And also, of course, energy cost. When the model is complex, you need to spend lots of memory and CPU for detection or work. So that's called dimensionality. So in robotics, for example, a mobile try to collect 20 features from LiDAR and 10 features from IMU, and instead of using these 30 features, we can project them to, as I mentioned, principal components. This is something that we're going to use in practice in some assignment. So instead of using X, for example, as a raw data coming from LiDAR or IMU, we can use principal component of that. Principal component is a mathematical, form, is a mathematical technique that instead of using raw data, you can get meaning out of data. Or because in PCA, principal component analysis actually is PCA. You are finding some axes out of data that they are orthogonal. They are orthogonal. When they are orthogonal, it means they are not correlating. They don't correlate. When you multiply them together, it becomes 0. They are not correlating each other. So that's the best features. Because if features correlate each other, one of them is enough. Why we have multiple features if they are correlated? So that's why we can use principal components to find the best features that are not correlating with each other. And find the best, actually, the components, principal components of those data. That's one of them. That's what we can use in robotics to decrease the dimension of the system. Decreasing dimension, as I mentioned, has so much benefits. You can make system faster, you can make it more stable, and instead of capturing noise or outliers, you can capture patterns or a structure of the system. Another thing is regularization. We have different regularization, but most of them working with norm. We already explained what is norm. Norm is when you want to find the magnitude of the vector, you use norm. We have different norm, norm 1, norm 2, and we can use norm for regularization. And what is regularization? Regularization means give more actually penalty to bigger weights. So controlling the size of the weights in general. We want to control the size of the weight. Can we bring that to optimization? Yes. When we optimize, when we find loss function, we can add some part in the loss function to choose the weights that are smaller. So this is what's called regularization. So regularization is actually controlling the size of the weight in training part, in learning step. That's very interesting. So, so we add penalty to loss function. We add penalty to loss function for bigger actually weights. So in the loss function, instead of just being data loss, we have penalty on weight as well. However, we put a coefficient, lambda, see how much regularization you need. If the lambda is bigger, so it means you penalize more bigger weights. Bigger weights need to get penalized. Give more penalty to the bigger weights. And then the last function is that this penalty on weights is a function of weights. And this is function of weights as well. So it means when you do derivative, they are considered, and the weight that coming out after that optimization is this a minimum weight, is the weight that is also it's not gonna make overfitting. That's what I want to say at the end. Okay, so the lambda is regularization strength, and the penalty can be used for norm 1 or norm 2. L1 or L2 is the name of two norms that we are using. Any question? I didn't ask you anything today. You get what I said today? What was the main point? The main point was kind of sometimes we have too much features, or the features are not good enough. They are correlated each other. We said, I want at the end of this class, at least you get this part, that if the features are correlated, we need to get rid of some of them. Principal components are one method. Another method is this. Another method, we are choosing the weights, the best weights, smallest weights. And smallest weights means less complex system. So how we do that, we bring a penalty for higher weights. We put that in loss function. As you can see, the loss is not just data loss that we had before. We also have a penalty on weight. However, we have a coefficient lambda always. Say, okay, how much? We can make it, we can play with that. That's why regularization is a method of controlling the weight of size of the weight. So we have two regularization. Yes.
How is lambda chosen? How is lambda chosen?
Lambda is called hyperparameters. Hyperparameters is a parameters that you need to choose, unfortunately. You know, like as a designer, based off the system we choose. Some parameters in the system are like that. They called hyperparameters. It was one slide here, I removed that, but I'm gonna talk about hyperparameters. These parameters are the type of parameters that we as a robotic engineer or whatever in the system design that. One of them is that we want to see how much we give this strength to regularization. Yes, this is something that we need to choose. We had more hyperparameters. Anybody can say more hyperparameters so far we said? Like one of them was the size of hidden layers. Size of hidden layers you choose in that exercise that you did. That's something else that there is more if I remember. Yeah, those parameters called hyperparameters. The hyperparameters are something that we need to choose as a designer based off the system. How complex is the system and how much, yes, this is something that we need. This is with tuning. You need to do tuning multiple times and choose them. They are hyperparameters because you designed, because they are general enough. They are general enough, you know. If, for example, you choose based off the system, if you give, for example, 50% penalty to weights for that specific system, you don't need to change it if take this robot to another room. You know what I'm saying? Those parameters not changing if you change the robot to some other environment. Instead of having carpet, have tiles. You're not supposed to change lambda. But very good question. Thank you for asking that. But we're going to talk about hyperparameters next class as well, a little bit. And L2 is just, it's called also reach. And the formula is a square of norm 2. You know norm 2 is a distance, actually. And you do a square of that. And this is, it means you are, give more penalty to higher weight because you are squaring that. That's why we also have another regularization called lasso or lasso. This is also very important in machine learning and these things. In this case, you just add absolute values instead of squares. You just add actually absolute values together and put these absolute values in loss function. Okay, so let's see. So normally norm, so here I draw two circles, like this big circle because the smaller circle. It has so many meanings, but the, the main meaning is that you want to have weights, smaller weights. Smaller weights makes the system more generalized and not complex. How control the norm? So to avoid overfitting, we add regularization term that penalize large weight to or optimization problem. Instead of minimizing training loss, we minimize training loss plus lambda 2. I don't know why we put divided by 2 here. I didn't check why we have that, but probably if you don't put that here, it still works. Maybe we put that when we get derivative, that is square 2 coming and get cancel out. Maybe because of that. There's no reason because lambda is something that you choose. You can choose it kind of that instead of having lambda over 2, you can have lambda prime. The same. It's just a constant value. But here is for actually norm 2. This is norm 2. For norm 1, that is just absolute value of those. You don't have this, and it's just absolute value. You don't have this, and we have 1 here. If we don't mention the number of norm, it means it's norm 2. Because norm 2 is so popular, we put a 2 here, means it's norm 2. when you don't put that 2, means it's already norm 2. So that's for regularization term. So the rest is similar. We do derivative from this, and we find weight based off that. So the weight, the new weight coming from the weight. Oh, okay, I got it. Why we put 2 here? When we get derivative, these 2 cancel out this other, and this come out. So this lambda W just get clear out to just add with that. So that's why. So as you can see, regularization not supposed to add complexity to the model. As you can see here, you easily add that to weight. You easily just add that to the weight. It's not makes the system so complex. So derivative is very easy to compute. That's why we put that 2. So if it's a square root, if it's a norm 2, a square of norm 2, this 2 gonna cancel out that 2, and this part gonna get out. So in general, this encourage the model to keep weights small. So the smaller weight means more general weight. Done. I even finished it earlier. Okay, yeah. So any questions? We have still a couple of minutes time. Any questions? Okay, so what we covered, it was the important part. Generalization is very important. We're gonna have one assignment regarding that. Finding accuracy for your assignment, for one of your assignment, because many people ask me how we can find accuracy, because I asked accuracy in the, but you couldn't find it because it was a data set that is already was there. You didn't make that data set. If you couldn't find that, that's okay. Without accuracy, just with if you put pictures, okay. And we talk about actually hypothesis class and effect of hypothesis class size. Yeah, I think I covered all the classes I wanted to cover today. Okay, so have a good day then. See you Friday. Friday we're gonna start deep learning. Right.